তো ফার্স্ট আমরা যেটা দিয়ে শুরু করছি সেটা হচ্ছে তোমার ইলেকট্রোম্যাগনেটিক ওয়েভস। এটা থেকে শুরু করলাম, কিন্তু আমরা এখানে আসলে বেসিক রিলেশন ওয়েভসেরই রিফ্র্যাকশন আমরা সেটা শিখছি। তো ফার্স্ট যদি স্টার্ট করি ইলেকট্রোম্যাগনেটিক ওয়েভস, তার আগে আপনাদেরকে আমি শিখিয়েছিলাম যে ওয়েভসের ক্লাসিফিকেশন তিন ভাবে করা যায়। In terms of direction of vibration with respect to the direction of propagation, মানে ওয়েভ যেদিকে যাচ্ছে তার রেসপেক্টে ভাইব্রেশন কোন ডিরেকশন হচ্ছে সেটার উপর বেস করে ওয়েভ টু টাইপস, ট্রান্সভার্স, লংজিটিউডাল, এটা আমরা শিখেছি। এরপরে ইন টার্মস অফ প্রপাগেশন, শুধু এই ওয়েভটি প্রপাগেট করতে পারছে না, ভার্সন ছিল ভার্সন, তাহলে তো ক্যাটার করা সহজ। কোথায় ছিল? তো ফার্স্ট যেটা বলছিলাম আমরা তোমার ওয়েভসের ক্লাসিফিকেশন নিয়ে, ইন টার্মস অফ দেখেন ওয়েভসের ক্লাসিফিকেশন আমরা কি করেছিল, we classify the waves in three different ways. First of all, in terms of direction of vibration with respect to the direction of propagation. Okay, the direction in which the vibration is taking place with respect to the direction of the progress of wave. The waves can be classified into two types: transverse and longitudinal. In case of transverse waves, the vibration takes place at right angles to the direction of propagation. If the wave is propagating this way or progressing this way, the vibration is taking place perpendicular to the direction of the propagation. This is transverse wave. And in case of longitudinal waves, the vibration is taking place parallelly or along the direction, right? If the wave is moving this way, the vibration is taking parallelly to the direction of the wave. This is longitudinal waves. Okay, we have actually explained all those stuff. Now, in terms of propagation, whether the wave can propagate or not, wave can be classified into two types: standing waves and progressive waves. Standing, other name stationary waves. Standing waves or stationary waves, and progressive waves. In case of progressive waves, the wave profile can move. Wave profile means the positions of crest and trough. The position of crest and trough move. For example, you displace water here, the crest, trough, then the crest, trough. So the position of crest and trough actually moving. This is progressive waves. And by the overlapping of two progressive waves coming from opposite direction having the same amplitude and frequency, we know a standing wave is produced. For example, two progressive waves, those have the same amplitude and frequency. When they meet each other from opposite direction, they produce a standing waves where the position of nodes and the nodes not moving. That means the positions of the crest and trough are not moving. This type of wave produced on girdle spring, on air column, right? This is a standing waves, example of standing waves. Okay, there are two ways we can classify waves. First, in terms of direction of vibration with respect to the direction of propagation. Second, in terms of propagation only. And a third, in terms of requirement of medium, whether the wave requires medium to travel through. You can classify waves in two types: mechanical waves and electromagnetic waves. For mechanical waves, the waves require medium to travel through. Without medium, they cannot travel. Lots of examples: sound waves, it can't travel without medium. Water waves, can you imagine water waves without water? No. Rope waves, waves produced on a silky spring, tsunami waves or seismic waves, these waves cannot travel through without medium. These are mechanical waves. And in this case, for these mechanical waves, when the wave propagate or wave travels, the system here is the actually particle of the medium. When the water wave is moving, the water molecule is vibrating. When you produce a wave on a rope, the rope matter is vibrating, right? In case of sound waves, when you speak or any sound travels through air or solid or liquid, the medium, the part of the medium vibrates along the direction of the wave. So, for all these mechanical waves, the vibrating system is the material, the matter particle, right? But for electromagnetic waves, no matter particle vibrates. Here, of course, there are vibrations. Since it's these are waves, there must be vibrations. But in case, just imagine sound, light traveling through vacuum. Light traveling through vacuum. There's no medium present there, right? But the light is propagating, it is moving. So what actually vibrates in this case? In case of electromagnetic waves, what actually vibrates? When the wave is moving through vacuum, even when these waves travel through other medium, if they can, they do not make the medium to vibrate. Here the vibrating system is not the particle of the medium. Here the vibrating system is an electric field and a magnetic field. Like this. Direction of wave or direction of energy transfer, right? And there is an electric field at right angles, vibrating electric field, and a vibrating magnetic field, which is also perpendicular to the direction of wave and the direction of electric field, and which is continuously alternating. Just imagine this is the direction of any electromagnetic waves. Okay, perpendicularly an electric field oscillating, and magnetic field, another field perpendicularly oscillating. So this is actually like wave progressing this way, electric field oscillating perpendicularly to the direction, and also a magnetic field oscillating perpendicularly again to the direction. So both fields are oscillating perpendicularly to the direction of the energy transfer or direction of the wave. And since there is an electric field and a magnetic field in this case, we classify those waves as electromagnetic waves. Visible light, UV, X-rays, gamma rays, radio waves, microwaves, all these are electromagnetic waves. And actually, why there is an electric field? If you ask me what is the mass of a photon, the particle of light. So photon is not a matter particle. It doesn't have any mass. The book says, if you search, you'll find that the mass of photon is 0, the charge of photon is 0, but this is not the whole scenario. If you ask me, I'll answer that the rest mass of the photon is 0. The rest charge of the photon is 0. I never say the mass of photon is 0. The photon doesn't have any mass. I would never say. I would say the rest mass. If the photon is at rest, if it is considered at rest, then you can say that it has no mass, but it has momentum. So if something has momentum, it must have mass. And we use that momentum to actually operate a light sail. Okay, space probe. Light sail is space probe. So it has a highly reflecting surface, and you can increase its speed just incident light on the reflecting surface from the earth. You can control it. If you just project light on the surface, the light actually hits the surface and returns back. So there is a change in momentum. The light has got a change in momentum this way. Therefore, to conserve the momentum, the light cell has undergone a change in momentum in the opposite direction. So it speeds up, and it actually works. It works. So light has got a momentum. There is a formula for that. You are considering that, and it is experimentally proven the light has got a momentum. Then, after saying this, you are saying light has no mass. This is contradictory. Light, of course, has a mass and has a charge, the photon particle, when it's moving. Of course, it will be moving, right? It's not stationary. But you can say the rest mass and rest charge zero, but not the actual mass or actual charge. It has mass in mega per c square. So it is again a particle. Particle of what? Energy. Energy particle, not matter particle. That's why people say that it doesn't have any mass. But energy particles actually do have mass. do have mass. Okay, so light has the mass and charge. So since it is a charge,